recall the partial differential equation to describe flow, and this could be from a reservoir into a wellbore, or it could be an aquifer into a reservoir. So it's from an outer cylinder into an inner cylinder. So again, I like my analogy of a roll of paper towels here. This inner cylinder could be the wellbore, the outer cylinder could be the reservoir, or the inner cylinder could be the reservoir and the outer cylinder could be the aquifer. The geometries are very analogous. In either case, what we have is the diffusivity equation in radial coordinates. And you learned this in Reservoir 1, and it's in the review video that I posted. So you might want to go back and look at this. So what this says is the pressure is a function of time and radius. You can derive that. We're not going to do it today. You can write this in dimensionless form. So the dimensionless pressure with respect to dimensionless time is equal to 1 over the dimensionless radius, RD. Okay, alpha is called the diffusivity constant. It's the permeability divided by the viscosity, porosity times the total compressibility, and that has units of like feet squared per day, length squared per time. Okay. So this is the dimensionless form. I should point out that the dimensionless pressure is related to the pressure, 2 pi kh times the initial pressure minus the current pressure divided by the production rate if it's a wellbore, or the encroachment rate if it's flow from an aquifer. Mu is the viscosity, B is the formation volume factor. RD is the dimensionless radius, which is R divided by R, the outer radius, which if it's an aquifer would be R over RA. And TD is going to be alpha, that's the diffusivity constant, times T divided by the radius of the reservoir squared. Okay, so TD is proportional to time, RD is proportional to radius, PD is related to pressure. Those are dimensionless variables. Okay, and again, we like to use dimensionless equations from time to time because we could have a solution or a table or a plot that's very generic and works regardless of the actual permeability and thickness and porosity of the reservoir, for example. Now what we want to do is we want to solve this PDE to get, so we say solve the PDE to get P of R of T. So it's a pressure as a function of radius and of time. So the pressure is changing with space and time. Or we might want Q of T, right? So that might be Q into the wellbore or Q into the reservoir from an aquifer. That's a rate. And rate we know is related to pressure gradient from Darcy's law. So if you have pressure, you might be able to get Q. Or, that's a rate. We might want the cumulative amount of water encroach from the aquifer to the reservoir. So that would be WE of T, which is the integral over the 0 to T of Q of T dt, right? So a solution to that PDE could give us any of those three things. Reservoir 1, I was maybe most concerned with the pressure or maybe the rate. Today, we're going to be most concerned with this cumulative water influx, much like the last week where we've been discussing this. To solve the PDE, you need an initial condition. And the initial condition, or a good approximation for that, would be the pressure at all radii at T is equal to 0 is equal to PI, right? And so that would be the initial pressure in the reservoir. You can estimate that from the hydrostatic gradient, so rho GH, right? Density of the water times the gravitational force times the depth. Or if you want a more accurate estimate, what you would probably do is When you first drill your well bore, you would have pressure gauges in there, and it would tell you what the pressure is at reservoir conditions initially. So we've got that. That's the initial condition. Then there's going to be a boundary condition that says at very far distances, like at r is equal to infinity or at the very edge of the reservoir. This presumes that it's a very big reservoir. At time is equal to 0, or another way of saying that is P is equal to PI far from the, I'll say the inner cylinder. Right? That inner cylinder could be the well or the reservoir, depending on your application. What that basically says is that if you're producing fluids, if fluids is coming in, the pressure will change near the wellbore, near your inner cylinder, but far, far, far away, the pressure won't change. In fact, we call that infinite acting flow. Okay. And this would kind of indicate more of a closed reservoir. So this is the boundary condition we might use. And then the last boundary condition is not far from the well or not far from the edge of our outer cylinder, but it's actually at the inner cylinder. So one boundary condition could be we have a constant rate. Okay, this is what we used in Reservoir 1. This is what you learned in Dr. Song's class. This is what I discuss in the video. And the constant rate says that at the wellbore, or at the inner cylinder, I should say, you have a constant rate, like QW mu 2 pi kh. Okay. That might look a little weird, but that's basically Darcy's law on radial coordinates. So the rate is proportional to the pressure gradient. So at a constant rate, if you had a constant rate well, you'd be specifying the rate that comes out, and that doesn't change with time. So that might be 1,000 barrels per day. Okay. That is the boundary condition I use in the video that you almost definitely used in Reservoir 1. It has an analytical solution. That analytical solution is the exponential integral solution. Okay. But there's another boundary condition we could put on there. Instead of having constant rate, we could have constant pressure. We have a constant bottom hole pressure, for example, of the well. So we can say that that's constant PWF, that's bottom hole pressure, BHP. So P at the inner cylinder, like the well bore, is equal to, again, PWF. All right. So this was Reservoir 1. This is today. Okay. You could, if we're talking about flow in a well bore, you could do either, and we do both. Sometimes we operate at constant rate, sometimes we operate at constant bottom hole pressure. They are both important. They have different solutions. The solutions, the first one was the dimensionless pressure is equal to minus 1/2 the exponential integral over minus RD squared over 4D to 4TD, right? This is the solution for a constant rate well. Now, if you're anything like me, the first time you saw this, it was a little intimidating, right? You've probably never seen the exponential integral before. This was a little daunting. You had to get used to it. If you recall that there were some approximations that involved logarithms, made it a little bit simpler. But the truth is that this is the easier of the two solutions. That's one of the reasons why when I teach Reservoir 1, I teach that solution but not the other one. But I can't really get away in this class by avoiding it. So what is Q of T for a constant bottom hole pressure well, or constant pressure inner cylinder, or the integral of that, which is WE of T? Well, it's complicated. Okay, it's a little bit complicated. I'm going to show you the solutions. There's 4 ways we could look at the solution. So the first one is the full solution. It involves Bessel functions. Now, I am going to bet that with maybe a few exceptions, maybe a few of you are math minors or something, most of you probably have never seen Bessel functions before. Okay, it's a complicated solution. I'll show it. We won't really use that one because it's so complicated. The second one is approximate solutions. Okay, they're pretty good. A lot easier to use than these Bessel functions. Another is graphs. Those are pretty easy to use. They're not as accurate because you actually have to, you have to read the graph off. And then the last one is tables. So what people have done is they have solved the full solution and presented the results in graphs or tables. You could use either one of those, and I'll show both of those. So the diffusivity equation in cylindrical coordinates was given here. So there's a spatial or radial dependence, and then there's a time dependence of pressure. You could write that in dimensionless form as I did before. So you got PD, RD, and TD. The solution for that, for infinite acting flow and a constant rate well, is given here. Okay, you should have learned this in Reservoir 1. I know I talk about it in the review video. Okay, it looks intimidating, but EI is just a function. Okay, and if you go into Excel or Python, or even if you just Google the exponential integral of something, it'll spit something back. Probably sophisticated calculators have it. The boundary conditions that we used were the pressure initially is equal to PI. The pressure far from the well was equal to PI. Okay, basically it's so far away that it's unaffected by what's happening in the wellbore. And then finally, at the wellbore, we have a constant rate condition. So basically says as R goes to 0 or R is equal to RW, which is essentially 0, you have a constant rate Q. So maybe you're producing 1,000 barrels per day. So that was the solution we used in Reservoir 1. I'm just showing that as a reminder, but we can't use that for what we want to do next. We're not going to have a constant rate in the inner cylinder. Instead, we'll have a constant pressure, or approximately a constant pressure. So what if we have a constant pressure in the inner cylinder? So let's say in that inner cylinder could be the wellbore or it could be the reservoir, depending on your application. Of course, we care about a reservoir with an outside aquifer. So the PDE doesn't change. The PDE is the same as what we had before, but our boundary conditions are different. Okay, and here's a reminder of what RD, TD, and PDE are. Those are the dimensionless values. Remember that now the reservoir is the inner cylinder, the aquifer is the outer cylinder. We want a solution that applies for all flow regimes. That's infinite acting flow and stabilized or pseudo-steady state. So that's early times when the outer boundary is unaffected by what happens in the inner cylinder, as well as late times where it is affected. And again, I review what infinite acting flow and stabilized flow are in the video. Instead of a constant rate boundary condition, meaning a constant rate in the inner cylinder, we're now going to assume that the reservoir is at constant pressure. And at that constant pressure, we want to know how much water flows from the aquifer into the reservoir. So the rate, or really what we want, is the cumulative amount WE. And so those boundary conditions look as follows. So the initial pressure is still PI. We have a boundary condition that says that dPdR is equal to 0 at the edge of the aquifer. What that really means is that the aquifer is closed, that nothing comes in or out of that boundary, right? It's like a wall, okay? But the most important boundary condition that's new here is that we're going to assume in that inner cylinder the pressure is constant, PE, at least for a period of time. Okay, so that's the pressure at in the reservoir or the reservoir aquifer interface, and that's going to be equal to a constant. That solution is completely different than the exponential integral solution. Okay, and that's of course characteristic with PDEs and ODEs. You can have the same differential equation but different boundary conditions and you'll get a completely different solution. They might not even look alike. So someone has solved this. It wasn't me. Okay, I'd have to really go back and review all the math that I learned really in graduate school to be able to solve this. It's complicated. This is what the solution looks like. I wasn't exaggerating when I said it was complicated. This might look like Greek to you, okay? You have this summation, which goes from 1 to infinity. You've got these J1 and J0, which maybe you haven't seen before. They're called Bessel functions. And this AN is the roots of this Bessel function. So it's like a, it's not a quadratic formula, but it's something like that. It's this complicated equation. You want to find the value of AN that makes this equation equal to 0. These Bessel functions, J0, J1, Y0, Y1, are called Bessel functions of the first and second kind. Basically, they're just functions. They're functions like the sine, the cosine, the tangent of x, or the exponential integral of x, or any other function you've ever learned. Okay, this is just new to you, right? So you'd have to use it and get a little bit more familiar with it, and then it would become second nature like sine and cosine are for you. I show you this just to show you how complicated it is. We're not going to use it. Okay, if I was really mean, I might ask you to write a Python code to code this up and come up with a solution, but I'm not going to ask you to do that. There are easier ways to evaluate WE at different radii in time, and we're going to learn those in the next one. This is the exact solution, and people have coded it up, and there's programs that use it so that you don't have to code it up, but this is the solution. I would like to point out one interesting thing about this equation, though. In that red area, I see that WED is equal to RED squared minus 1 divided by 2. That should look familiar to you. That is the solution for the small pot aquifer. Remember I said that the small pot aquifer only works if you've got small radii or very long times, right? A small aquifer, or if you go to very long enough times, that would be the ultimate recovery. And so, and actually, if you say TD, the dimensionless time is very big, like infinity, e to the minus infinity or e to the minus a very big number is 0, so this whole term is 0, and you just get this. So it's definitely interesting. And it kind of validates what we had said before, is that if you go to long times, or if you have a small aquifer, then you don't need this infinite term, and then you're just left with this part. So really the small aquifer is a special case of this analytical solution. Okay, but with that said, I don't want to use this equation. It's ugly. I've got an infinite series. I've got these Bessel functions, which I'm not super familiar with. I'd have to find the roots of this ugly equation here to get my AN. That seems tedious and difficult. So what people have done is they've come up with approximate ways or easier ways to evaluate WED as a function of dimensionless radius, RED, and dimensionless time, TD. One of those ways was given by Edwardson. So Edwardson et al., what they try to do is they said, well, you know what, I can solve that, but I don't really want to. What if we had an easier equation that I could just type into a calculator, okay, or something? Well, what he found, or what they found, is that WED, the dimensionless cumulative water influx, is a function of time by these formulas during infinite acting flow, but only during infinite acting flow. Remember, infinite acting flow effectively means early times before the outer boundary has the effect. So if you're at late times, you can't use this, but at early times you can. And so what Edwardson et al. Found was that if TD, the dimensionless time, is really small, less than 0.01, you could use this. If these are the criteria, if it's between 0.01 and 200 and TD is less than this, which is infinite acting flow, then you can use this equation. And if TD is a little bit bigger but still less than 0.25 RED squared, you can use this equation. Now, if TD is greater than 0.25 RED squared, you can't use any of these. So you're out of luck. We got to use something else. But these aren't super simple, but they're at least equations you can plug into a calculator or plug into Excel or plug into Python relatively easily without using the Bessel functions. And again, WED is the dimensionless water influx. You'll probably want to compute the dimensional water influx WE. And this would be very similar at this point to the example problem we did last Friday. And we worked on it together and you were able to get that. So Edwardson et al. Have these approximate solutions that don't use Bessel functions. They're still a little tedious. I mean, you gotta type a lot of things in there to get it to work, and maybe if you're not careful, you're likely to make a mistake. And then the worst part about this is that it's only good in infinite acting flow. So TD has to be less than 0.25 RED squared. Okay, so and if you remember, this 1.119 is equal to 2 pi divided by 5.61. 5.61 is a conversion constant to go from cubic feet to barrels. And here's a conversion constant as well. Note that T is in hours. Okay, well, maybe we don't want to use the Edwardson et al. Solution, or maybe we're not in infinite acting flow. So we can't use that anymore. Okay, well, there are graphical solutions of that. So this is pretty easy to use. WED versus TD is given by this plot over here. So given a TD, like 150, you can come up to your RED, that's the ratio of the aquifer to the reservoir radius, and you get the value. So over here it looks like it's about 42 or so, right? 44 maybe. That is that. Now, if your RED is really big, then that's the infinite acting flow solution. So that's RED is greater than 20 or so. You go technically all the way to infinity. That's the infinite acting flow solution. What that means is the aquifer radius is way bigger than the reservoir radius. In that case, you could use this solution, and this solution here, where RED is equal to infinity, should be very close to what you get over here. And so I'm not sure if I'll make you do that either, but a really good exercise would be to have you plot this up in these regions and then compare it to the RED is equal to infinity, because those should be almost identical. But WED is a function of TD as well as RED. I'd like to point out one other thing, is that as TD gets really big, long times, this sort of reaches an asymptote. Okay, it's there for both of these, it's almost there, it's not there yet for these top two. What is that asymptote? Well, it's RED squared minus 1 divided by 2. We've seen that before. That's the small pot aquifer. Okay, and remember, the small pot aquifer is the ultimate amount of water that would encroach if you waited long enough times. Okay, and RED is equal to 5 is pretty small. So that's why even at about 50 dimensionless time, you're already there. For RED is 20 or more, well, you got to wait till longer times. But this asymptote is RED squared minus 1. In fact, let's even put it in. 5. 5 squared is 25, minus 1 is 24, divided by 2 is 12. I come across, that looks like about 12. Okay. Now, a downside of these plots is that, it's hard to get an exact number, right? I mean, you can estimate that it's about 12 or something, but, might be hard to get 12.213. So that's one downside, although that's not a big deal. Usually we're looking for approximate values. By the way, it's 2021 now. You go on you go on the internet, you can very quickly find free software that digitizes plots like this. So, and when you digitize it, you can actually get a number that's actually with decimal points and all sorts of stuff like that. I won't ask you to do that more than likely in this class. If you use it on an exam, I would be okay with you coming up with an approximate result as long as it's reasonable. So that is WED from these plots. There's one last way to do it, and that's from tables. Okay, these are the tabulated solution of WED, and I put this on here, but I'm actually going to go to Canvas. And this is what the table is. Now, the nomenclature is a little bit different than what we're doing here. So they use QD instead of WED. They use capital Q to indicate it's cumulative rather than lowercase q. But of course, we mean WED. And let me, this is a little small, so I'm going to blow it up. And so if you're at infinite acting flow, and you can calculate that, whether your TD is big enough to be TD is small enough to be infinite acting flow, then for a given TD, you can come across and find QD or WED. I'm even going to do, let me do an example problem here. So let's go to here. Infinite acting flow is this RED is equal to infinity. So let's say TD is 150. Then at RD is equal to infinity, infinite acting flow, I would expect WED to be about 60. That's what the plot says. Let me see what the table says. TD is 150. There it is right over there. WED is 59.895. Well, that's really close to the 60 that I said. One advantage of the table is obviously that you get a little bit more accurate. You get more decimal places. Now, you might have a TD that's not exactly 150 or 155 or 160. If that's the case, you can interpolate. You know how to interpolate. You learned it in PG 310. You probably have used it before. You do a linear interpolation between those points, and it's going to be really close, right? So 150. Let's say it's 152. Well, it's between 59.895 and 61.517. So the answer is probably 60.5 or 61 or something. So and that would be close enough, but you can do an actual linear interpolation to get an exact result. Later times, where the outer boundary is having an impact. Well, there's a different table for that one. It's a longer table. And in that case, you have to determine what your RED is first. Just as a reminder, that's the ratio of the aquifer radius to the reservoir radius. And based on that, then you find your TD, and then you find your WED. Okay, they call it QD here, but it's WED. Let me see if I can do another example. Let's do TD is 150, but RED is 10. That looks like it's going to be about, I don't know, 43 or so. So RED is 10, TD is 150. Let me see if I can find that. RED is, well, it goes to 5. I got to go to the next page. There it is. RED is 10, TD is 150. What happens when I go to 150? Well, they don't have 150. They got 140 and 160. 140 is about 41, 160 is about 43. That means 150 is about 41, no, about 42, which is what I what I had found from the plot. So that's how you do that. And then I'd like to point out one other thing over here. On these, when you get to a point, it just stops. Okay, so if I go back to my plot over here, remember when RED is equal to 5? When you get to above about 50 or so, it asymptotes and is equal to the small pot aquifer, which we said for 5 would be 12. So WED would be 12. If I go over here, this was RED is equal to 5. and I come down, and once you get to about 50 or so, it's starting to level off at about 12. Once it gets to 100, it is 12, and they don't even go beyond 120 because it doesn't stop after that. Okay, you are now effectively a small pot aquifer. So with that, I'll say that those are the 4 ways to calculate this, to calculate WED. So the first way is to actually use the true analytical solution based on the Bessel functions. That seems very complicated. I don't expect to ask you to do that in this class. We could, but we probably won't. The next way is to use the approximate equations by Edwardson, which are, they're still complicated, but they use things like square roots and things that we're used to. But as a reminder that those are only valid in the infinite acting flow regime when the dimensionless time is small compared to the dimensionless radius. The third way is these plots, and the fourth way is the tables. So those are the 4 ways. I would expect to ask you to use the tables and the plots most. Maybe there would be something to where I'd ask you to use the Edwardson equation. We won't use the Bessel functions very much. But I should say that these tables and plots were based on the Bessel function solution. So somebody did all that work for you and then compiled the results in tables and graphs. Okay, so the next question. How do we apply this solution to aquifers? That's what we want, right? We want the cumulative amount of water encroached into the reservoir. And what we have now, any of the 4 ways we use it, is a solution for cumulative flow if the inner cylinder is at constant pressure. So if the reservoir was at constant pressure, then we could use the solution to figure out how much water came in cumulatively with time into the reservoir. So again, that's what we want. We want WED, or we really want is WE in dimensional form. Remember, that solution I showed you was originally proposed for a wellbore that had constant bottom hole pressure and an outer radius, which is the reservoir. We could use exactly the same solution. We're just going to make the inner cylinder the reservoir, the outer cylinder the aquifer. So we just need to be careful with that. And that's what I say again there, is that the outer radius is RA, the radius of the aquifer. But here's the most important point, is that solution I showed you in its current form is not applicable for aquifers. And here's why. Because the pressure of the reservoir is not really constant. The solution was based on a constant pressure in the reservoir. But the pressure in the reservoir is going to decrease with time. As you're producing fluids from the wellbore, the reservoir pressure will drop, and that will affect the solution from the aquifer into the reservoir. So I went through all that trouble to show you an analytical solution for a constant pressure in the inner cylinder. Now I'm telling you that the pressure in the inner cylinder is not constant. Well, it doesn't mean we can't use it. We just have to come up with a creative way to apply it. And that creative way is to use what's called the principle of superposition. I think you were introduced to the principle of superposition in Reservoir 1, maybe when you're talking about well testing, and you had the rates change with time. It's possible you were introduced to the principle of superposition in some of your math classes. But let me try to remind you what that is. The principle of superposition says that for some mathematical problems, not all, I'm not going to get into the details of it, it's basically problems that are linear. The important thing is that we can apply it in our case. for some mathematical problems, you can assume that that you can add a series of different problems to sum up. You can superimpose them on top of each other to get the original problem. So what do I mean by that? What I'm trying to say is that on the plot on the left here, at the initial time, we'll call it T0, the initial pressure of the reservoir is Pi. That was our initial condition. The pressure is going to decline with time. I don't know exactly how, but it looks something like this curve over here, right? And we'll have that data, right? Because again, we've got pressure gauges in our wells. Those will tell us what the pressure is a function of time, and we can assume that that pressure is equal to the reservoir pressure. So we have maybe Pi, P1, P2, P3 measured at T0, T1, T2, T3, and you know, those are discrete points, but you could draw a curve if you wanted to, and it would look like that. So clearly we don't have a constant pressure. Pressure of the reservoir is declining. So how can we use our constant pressure solution to do that? Well, what we're going to do is we're going to use discrete jumps. We're going to pretend like the pressure is constant from T0 to T1. Then it's going to change very quickly, and then it's going to be a different constant from T1 to T2, and then there'll be a constant from T2 to T3. And so over those periods of time, the reservoir pressure is constant, and we can utilize our solutions that we talked about. Then we're going to superimpose, that's why we call it the superposition, principle of superposition, each of these individual solutions. So to recap, the reservoir at the reservoir aquifer interface is initially Pi. Over time, the pressure decreases. We'll have data of that decrease. We approximate the pressure drops as these discrete drops. So delta P1, delta P2, and delta P3. These delta P's are the difference in the previous pressure to an average pressure between these two regions. And so I've depicted on how we do that. So what we have is delta P1 is equal to Pi minus P1 average. P1 average is the average pressure between Pi and P1. How do we calculate an average? Well, we just add them up and divide it by 2. So P1 is Pi plus P1. Both of those are going to be given from your pressure gauges. They'll be given in a table divided by 2. And if you combine this, you'll see it's equal to 1/2 Pi minus P1. Okay, that's delta P1. That's what we have here, right? What about delta P2? Delta P2 is going to be the average P1 minus the average P2. So average of P1 is Pi plus P1 divided by 2. P2 average is P1 plus P2 divided by 2. And then this simplifies to 1/2 Pi minus P2. If you notice, I made my negative sign red there. I did that because right before class I was looking and I realized I had a typo. There was a positive there, and that was on Canvas. So I've corrected it on my version. I'm going to look for a few more mistakes, a few more places for improvement, and I will eventually add that on there. But if you want to make a note that this is a negative here, then that would be good. Delta P3 is this delta P2, this P2 bar minus this P3 bar, which is given here, 1/2 P1 minus P3. And for any j that's greater than 3, or really greater than or equal to 3, delta Pj is 1/2 times Pj minus 2 minus Pj, right? So if j was 3, you'd have P1 minus P3. If j was 4, it'd be P2 minus P4, etc. Again, we've got these delta P's, which I've showed you on the previous slide. water encroaches during each of those times, and we can sum them up using the principle of superpositions. So what we do is we evaluate WED at a certain time, or delta T. Okay, and this TD is the final time that I'm interested in minus a current time, because I'm summing up from j is equal to 1 to a certain number of time steps, n. So you do this summation and you find WED. This is not being multiplied. What I mean by is a function here. So you calculate this TDN minus TDJ minus 1. At that delta T, you go to your graphs or your table or your Edwardson et al. Solution. You calculate WED. You multiply it by your delta PJ, where j is going from 1 to n, and our delta PJs are given by these equations up here. And then you do that from a summation from j is equal to 1 until the final time step that you're interested in. And you can sum that up and you multiply that by your u, which is given by this equation. We've seen it before, and you get the cumulative water encroached. So we're almost out of time. I'll very quickly explain this, and don't worry, we're going to come back to it. We're going to do some examples. But basically what you're going to be given is time, maybe in hours, and the pressure of the reservoir, which is here on the second term. That's the data you're given. Then what you do is you calculate your delta PJs using these equations. Then you calculate your delta T, which is given here. It's going to be your Tn minus T0, Tn minus T1, Tn minus T2, etc. You put it in dimensionless form, which is this equation over here. Then you, using your delta T, D, you go to your tables or your plots, or if you're really ambitious, use your Bessel function solution and calculate WED. And then at the end, you sum all those up. Okay, so that's a little much. I imagine that's a little complicated seeing that as the first time, but we're going to revisit it on Friday and maybe throughout next week, and we'll do at least one, if not multiple, example problems.